Welcome back to our system design series. Today we are going to talk about consensus algorithms, which are critical components in building reliable distributed systems. In a distributed environment where multiple nodes are working together to achieve a common goal, it's essential to maintain a consistent state across all nodes. But how do we do that? When dealing with challenges like network latency, node failures, and asynchronicity. This is where consensus algorithms come into play. So let's try to understand how it works. So let's assume that we have a system that contains multiple nodes. Let's say that we have node 1 and make it real big. And let's copy it. Let's assume that we have a distributed system. And we have node 1, node 2, node 3, and node 4. So in a distributed system, we have 4 nodes here. Nodes needs to work together to maintain a consistent state. However, due to the inherent challenges of distributed environments such as network issues, failures, and nodes potentially acting like maliciously, achieving this consistency isn't straightforward. It's pretty tough. And consensus algorithm address these challenges by ensuring that all participating nodes can agree on the same state or sequence of events, even when some nodes might fail or behave incorrectly. So let's assume that imagine a situation where a group of servers, as you can see right now here, when a group of servers, as you can see right now here, must agree on the value of a variable, like the balance in a bank account or the leader of a cluster. A consensus algorithm ensures that despite failures or communication issues, all nodes in the system agrees on this value, keeping the system consistent and fault tolerant. Okay, there are two popular algorithms. I will go with Paxos first, and after that maybe we can talk about another one. So on how does this work, how all of these nodes will agree on something. So um let's talk about the PEX algorithm. PEXO is one of the most famous consensus algorithms created by, I guess, something called Leslie Lamport. PEXO worked by electing a leader that processes a value which is then accepted by a majority of nodes in the system. So first, the first thing is leader election. Like, a leader is elected among the nodes, and this leader is responsible for proposing values, or we can say it's coordinator. Let's assume that we have node 1 is the leader. The second thing, we have a proposal phase. The leader propose a value that it thinks should be agreed on, like a new bank account or something like that, a new bank account value, or a new information about specific state about one of the nodes, something like that. So when I try to propose it, first thing we have the acceptance phase, like it will connect with the nodes, and then we will have some sort of acceptance phase, because the other nodes called acceptors vote on the proposed values. And after that, we have a majority agreement. Like, if the majority of the nodes accept the proposal, it becomes the chosen values. Paxos is known for being theoretically sound, but it also quite complex to implement in a real world system. It maintain it maintains strength. Its main strength is its ability to achieve consensus even in the face of failures. However, due to in its complexity, Paxos can be challenging to understand and maintain. The other thing, we have what we call a raft algorithm. And in the Raft algorithm, is another consistent algorithm created as alternative to Paxos. Raft aims to be more understandable while still providing the same guarantees. It works by designating one node as a leader, which is responsible for maintaining log replication and ensuring consistency across the cluster. So let's go again. We have a leader election. One of the nodes is elected to be the leader, as the leader is responsible for maintaining log entries and coordinating the cluster. You can refer to it as a coordinator. We have a log replication. So the leader receives updates like log entries from clients and replicates them to follower nodes. After that, we have a commit phase, like once a majority of nodes confirm that they have received the log entry, the leader commits it, ensuring that the entire cluster is in sync. So yeah, the Raft is designed to be simpler to understand and implement compared to the Paxos. It breaks down the consensus problem into smaller sub-problems, making it easier to reason about and yet use it in distributed systems. Um, okay, so let's try to understand the questions or answer the question about why consensus algorithm is important. The consensus algorithms are important essentially for maintaining a consistent state in the distributed system. I don't know if this is helped just by type every the first character of each word I say, but let's assume that it's really important in distributed systems like clusters, servers, or replicated state machines. Consistent algorithms ensure that all nodes agree on a critical state information, even if some nodes fail. This consistency is what allows distributed systems to be reliable and fault tolerant. Like without consensus algorithms, nodes in distributed systems could end up with conflicting views of the system state, leading to data inconsistency, errors, and potentially data loss. These algorithms are foundational for services that needs to maintain high availability and while ensuring as well data integrity. So yeah, that was a quick introduction to a consensus algorithm. If you like this video, make sure to subscribe and hit the notification bell so you'll never miss any video, and see you guys in future problems.